Hello, I'm Mansi Limbu. I'll be presenting our paper on scaling team coordination on graphs with reinforcement learning. Let's assume multiple agents are traversing an environment graph easy to reach a specific goal. Along the way, they can encounter multiple risky edges that can be mitigated with support from teammates at specific nodes to minimize the traversal cost. If agents take direct and risky route without assistance from teammates, they incur a very high cost in route to the goal. However, if agents use supporting behavior from their teammates, they can reduce overall team cost to reach the goal significantly. In the paper Team Coordination on Graphs with State-Dependent Edge Cost, Easy is transformed to a joint state graph called GSG to find the minimum cost solution. Another approach, Critical Joint State Graph (CJSG), addresses the computational inefficiency of GSG but is limited to two agents and simple graphs. This brings us to questions. Can GSG provide efficient solution if the number of agents increase and Easy become more complex? Can we get our desired solution as shown in the figure, where agents coordinate in risky path to minimize the team cost to reach the goal? Unfortunately, if we use JSC, it becomes computationally inefficient when facing more agents and larger graphs. Using naive shortest path algorithm, agents can quickly find shortest route to the goal, but this results in increased team cost as agents lack coordination in the risky edges. To address this limitation, we devised strategy that ensured not only scalability but also team coordination. In the first part of the paper, we address team coordination for multiple agents within a single easy by transforming the problem into Markov decision process, that is MDP, with states as joint agent positions and actions as the joint movements. In the second part of the paper, for any n-node graph, we address the team coordination by transforming problem as MDP. State space combines agent positions, graph connectivity, and support mechanisms, while the action space remain consistent with the single easy. We implemented masked queue learning that maintains a global queue table for joint states and joint actions but runs into combinatorial issues with increasing complexity of the problem. To address the limitation of queue learning, we implemented masked PPO, which is more sample efficient and has stable policy updates. In any n-node graph, actions in neighboring nodes are only considered valid. Both queue learning and PPO without masking consider all nodes as possible movements. To enforce restricted transitions to neighboring nodes only, we use invalid action masking. Next, we save our reward function to promote agent coordination and minimize team cost. We use high sparse reward as goal reward with small step cost. Movement reward is total individual costs incurred when traversing the edge. Coordination reward is for incentivizing coordination in the risky edges. The final reward is sum of goal, movement, and coordination reward. We found the weights for the reward terms through our experiments. For single easy experiment, we generated solution times for 2, 3, and 4 agents using JSG, queue learning, and PPO. We conducted the experiment for 5 to 25 node graphs with different densities, sparse, moderate, and dense. In this experiment, we found that RL's efficiency drops for larger problems, yet its advantage over JSC starts to emerge with complex graph and more agents. Next, we generated optimality versus time for single easy. Cost incurred by aging using JSC is used as the optimal cost for comparison. For 4 agents on a sparse graph, PPO excels over JSC in time and optimality in 15 node but not on a 10 nodes graph. On moderate and dense graphs, PPO strikes a balance between JSC and the naive in both 10 and 15 node graphs. For multiple eases, we generated optimality versus time for 2 agents. For 5 and 10 node graphs, Q-learning lagged in optimality and efficiency compared to GSG, while PPO achieved 70 to 80% optimal solution with half the time of GSG.